Hello class, welcome to 4.6 ratio and root tests. We have a couple of tests to help us determine if the series converges absolutely or diverges. And so I will go ahead and begin with the ratio test. So let summation n1 to infinity be a series with non-zero terms. Let rho be equal to limit n approaches infinity, absolute value of an plus 1 over an. Okay. Now this symbol you see here, it's a Greek letter and it's pronounced rho, R-H-O. So here are the conditions. If 0 less than or equal to rho less than 1, meaning if that limit value is a value between 0 and 1, 0 included, 1 not included, then summation an converges absolutely. Second condition, if rho is greater than 1 or if rho is equal to infinity, then summation an diverges. And the third condition is, if rho is equal to 1, the test does not provide any information. Typically, we will try a different test when we get to this point. So let's take a look at this problem. Use the ratio test to determine whether the series is convergent or divergent. So the first problem is that it's summation n1 to infinity 2 power n over n factorial. Since we are asked to use the ratio test, let's go ahead and assume rho to be limit absolute value of an plus 1 over an. So then we have to look at this given problem and determine what an will be. Okay. So in our problem, an is 2 power n over n factorial. That means an plus 1 must be 2 power n plus 1 over n plus 1 factorial. Okay. If you recall again the factorial property, the concept, n factorial is defined to be n times n minus 1 times n minus 2 and so on times 3 times 2 times 1, right? So it always starts from n and then goes down, multiplies by a number 1 less than the previous. So if n is 5, if it's 5 factorial, then it's 5 times 4 times 3 times 2 times 1. If it's 10 factorial, it's 10 times 9 times 8 times 7 and so on, all the way up to 1. And given that idea here, let's come back to the problem. So your rho now is limit n approaches infinity 2 power n absolute value of 2 power n plus 1 over n plus 1 factorial, that's your an, over 2 power n over n factorial, which is your an. So an plus 1 over an. Now we have to use algebraic techniques to break this down and simplify it. So first of all, let's take care of the complex fraction. Multiply by the reciprocal of the denominator. Then use the knowledge of laws of exponents to split up the 2 power n plus 1 as 2 power n times 2. And then the n plus 1 factorial is the same as n plus 1 times, the next one would have been n plus 1 minus 1. So n plus 1 minus 1 is n. And so you could say that the following terms that would multiply to this n plus 1 would give us the n factorial, right? So I can kind of show that to you here by the side. N plus 1 factorial is n plus 1 times n plus 1 minus 1 times n plus 1 minus 1 minus 1. You see that? We are subtracting 1 each time, and then it goes to 3, 2, and 1. So what we're saying is, well, we'll just keep the n plus 1, the first term, and then understand that this entire thing, that goes away, right? So it's n, let me bring that down here. So that's going to be n times n plus 1 minus, that goes away, so it's n minus 1 times n minus 2, etc. 3 times 2 times 1. And so this whole thing here would be your n factorial. So it's the same as rewriting the n plus 1 factorial as n plus 1 times n factorial. And that's what we're doing here in the step. Times n factorial over 2 power n. This gives us the ability to simplify the cancelling of these terms, and you can see that it quickly gives us an expression without the factorial, which makes it easy to compute. That reduces to 2 over n plus 1, absolute value. Now go ahead and divide, you can divide each term by n. So I'll just say divide by n, divide by n. Remember, we want the n in the denominator within the fraction, so we now have 2 over n. This is n over n, which is going to be 1, plus 1 over n. And now you can see very clearly that as n approaches infinity, you get 0 on the top, 0 over 1 plus 0, so 0 over 1 is what you get when you evaluate, of course, the absolute value, but you know that is 0. Now go back to the ratio test, which gave us those 3 properties. If rho is, we got rho as 1, so if you look at the first condition accepts 0, okay? So if rho is between 0 and 1, 0 included, then we can say that it converges absolutely, and we're going to call upon this first condition here and say since rho is equal to 0, it implies summation n 1 to infinity 2 power n over n factorial converges absolutely. Let's look at problem B. This is summation n power n over n factorial. Let's try the same technique. Our an will be n power n over n factorial, and an plus 1 would be n plus 1 here. Wherever n is, you add a 1 to it. So it's n plus 1 power n plus 1 over n plus 1 factorial. Therefore our row, which is limit n approaches infinity, absolute value of a n plus 1 over a n. Now we can substitute for those places. Like we did previously, it's a complex fraction, so numerator times reciprocal of the denominator. And the numerator here can be split as n plus 1 power n times n plus 1 power 1. Right? It's just n plus 1 over, and the factorial is like before, n plus 1 times n factorial. And here you have on the other fraction n factorial over n power n. So see that this n plus 1, n factorial, they all go away. This leaves us with n plus 1 power n over n factorial, n power n. They both have the same power n, which allows us to use laws of exponents to write them as a single fraction with a common power n. And here within the fraction, divide up and down by n, because again you want the n in the denominator of the fractional setup. One over n plus, because you're dividing the first term by n, that'll be n over n, which is 1, plus 1 over n over n, which is 1, right? You divide up and down by n, right? You can't just do one of them, you have to balance it. So 1 plus 1 over n, the whole power n. The denominator 1 can be left like this. Now n is a positive integer, isn't it? Therefore 1 plus 1 over n will be a positive expression. That raised to the power n will also be positive because n is positive. And we know that if n is a fraction, n is a positive integer, so we don't have the condition of n being a fraction. And therefore we can drop the absolute value bars. Okay. So I'll just say since n is a positive integer, value bars. All right. Then we simply have limit n approaches infinity 1 plus 1 over n, the whole power n. And we know that this actually is our e, right? This value here. This is the definition of e actually. This approaches e as n approaches infinity. Something we've learned in algebra when we spoke about the natural base e. Okay. E approaches, 1 plus, this is what we learned, 1 plus 1 over x, x properly, 1 over 1 plus 1 over x power x approaches e as x approaches infinity. This is the definition of e. And so when you apply limit, we see that this will be equal to e. E is approximately 2.7. We know that, right? Because it's an irrational number, so it's not going to end, but we're just like writing the approximate value so that we will know what rho is. And rho is a value that is more than 1. Okay, so let's come here to the conditions. So if rho is more than 1, then the series diverges. That's what the condition says. The second condition works here. So we'll come back here and say, since rho is greater than 1, it implies summation n 1 to infinity n power n over n factorial diverges. And here's the third problem. Alright, this looks a little more complicated. We have summation -1 power n factorial squared over 2n factorial. Okay, the 2n is together. Okay, they wanted us to use the ratio test, so we'll go ahead and complete it that way. An is this whole thing that's inside the summation. Okay, and then a n plus 1, wherever n is, you have to write n plus 1. So I'll put a, because there's a parenthesis, I'll put a bracket here to show that that's being squared. And then it's 2 times n plus 1 together that gets the factorial. You have to be super careful here, because you're simply replacing n by n plus 1. So all other positions must be carefully assigned. For instance, the square and the factorial must all be in their right positions. Okay. This is going to need a lot of space because we now have a huge expression. So let's start here from the leftmost end. Rho says that its limit absolute value of an plus 1 over an, n approaches infinity, is the setup. And so let's write this huge expression for an plus 1. Over an okay. As much as this looks intimidating, remember that your algebra simplification is what is really required here. So take it systematically. The first step is, of course, to take care of the complex fraction. Okay. -1 power n times -1, right? Splitting that up. But also remember, this -1 would return as a positive because of the absolute value. So let's keep that in mind. Okay. And here, you split that up and remember to put the square. Okay, for this one, I want to do a quick story by the side here. Remember that this is 2 times n plus 1, whole thing factorial, right? So distribute the 2 to n plus 1, 2n plus 2 factorial, right? And if you expand this factorial, it's 2n plus, keep writing the 1, 2n plus 2 times 2n plus 2 minus 1, right? Times 2n plus 2 minus 2 times 2n plus 2 minus 3, etc. up times 3 times 2 times 1 until you reach that, isn't it? So let's simplify this. So that's going to be 2n plus 2 times 2n plus 1, and in this point you see that these two will go away. That gives you 2n times 2n minus 1, this would be plus 2 minus 3, and so on, 3 times 2 times 1. But then we can see that this whole thing, not there, this whole thing here, that is 2n factorial, right? Because that's 2n times 2n minus 1 times 2n minus 2 and so on. So use that same idea, but we're expanding it for a couple more steps. So it's 2n plus 2 times 2n plus 1 times 2n factorial. That's what this reduces to. And so I'm bringing that information into my step, and I would say 2n plus 2 times 2n plus 1 times 2n factorial. And here we have 2n factorial over negative 1 power n factorial squared. Okay. For that matter, I want to come back here, okay, and we have n plus 1 times n factorial the whole squared. We could actually square them individually, okay, just that it's easier. So I'm going to separate them. They were individually squared, so I'm going to separate them right there in that step. I don't want to go one more step to expand that. You can always pause the video and see what how I split it up. Alright, now it's time to cancel off all the common terms up and down. This whole thing goes away. Squared and the squared. Okay, it looks like we have, well, the negative 1, this becomes positive in absolute value bars, right? That becomes positive there. And so that is also taken care of. So we have limit n approaches infinity, absolute value of n plus 1 the whole square over 2n plus 2 times 2n plus 1. This is all we have left in the absolute bars. Okay, now it's time to again use algebra and expand this, because we have to apply infinity for n. So expand this. You can use a plus b the whole squared formula, which is a squared plus b squared plus 2ab, or you could multiply it twice and FOIL. This is what you will get upon expansion, n squared plus 2n plus 1. Okay. Over, again, FOIL the denominator, so that's going to be 4n squared. 2n plus 4n, so that will make it plus 6n plus 2 times 1, just 2. We got this. Alright, now within the within the absolute value bar, remember to divide by n squared up and down. So what we get is 1 plus 2 over n plus 1 over n squared, right? For the 2n over n squared, the n and the n squared n will cancel off, leaving us with one extra n at the bottom. And this would be 4 plus 6 over n plus 2 over n squared. Very, very desired condition, because now you have the ability to apply the limit. When you apply the limit, this becomes 0, this also becomes 0. So we are ultimately left with 1 over 4, absolute value of 1 over 4, which is simply 1 over 4 because 1 over 4 is positive already. Alright, so now we have to go back. 1 over 4 is a value less than 1. So let's go all the way back to the rule. So if your row is less than 1, which is the first condition, right? If it's less than 1, then AN converges absolutely. So we got that. Let's come back here and declare that. Since row is less than 1, it implies the original question converges absolutely. Okay, I hope that was fun. Now let's move to root test. Consider a series summation an n1 to infinity. Here we use the row again, but remember this is root test, so we're going to adjust our row for the root. And root means the radical, right? The nth root of absolute value of an. Okay? That will be our row. Again, we have 3 conditions. If row is between 0 and 1, 0 included. Summation an converges absolutely. If row is greater than 1, or if row is equal to infinity, then an diverges. Thirdly, if row equals 1, no information. So let's take a look at our first problem. Use the root test to determine whether the series converges or diverges. And the first question is summation n squared plus 3n the whole power n over 7n squared plus 5 power n. Okay, let's start with row. You have the power n, right? Power over and power. So we want to start with the root test. Because we understand that the root and the power will undo each other, right? If you have a square as the power, square root will undo it. If you have cube as the power, cube root will undo it, and so on. So we have n as the power, so nth root will undo it. Okay. An. We know that an in this problem would be n squared plus 3n that will be our an. So go ahead and pull that in the place of an in your radicand. Radicand is the expression under the radical symbol. So absolute value of make this radical even longer. Okay. Now make a quick observation. Now your n is always a positive integer, we know that. If you looked at the focus on the radicand, you have n squared, so it's going to be positive, plus 3n. We know n is positive, so 3 times n would also be positive. With the plus sign, the numerator is going to be positive. With a power n, n is also positive. So things are good there. Similarly, for the denominator, n squared means it's going to be positive. 7 times n squared is positive, plus 5 is going to give us a positive expression raised to the power n. Because of these reasons, we can drop the absolute value bars. So we'll say drop absolute value bars since radicand is positive. This is very important, we know that, right? Especially the absolute value under the radical is very important because you can't accept a negative radicand if the root is even. Square roots, fourth root, sixth root, they cannot accept negative radicands, but odd roots can accept negative radicands. So to accommodate both these options, the oddness or the evenness of the power and the root, we bring in the absolute value. In this case, we are very certain that this is going to be a positive radicand, so we are cautiously checking everything before we drop the absolute value bars. Okay. So this step, I'm not doing any operation. I just want to show the absolute value bars being dropped. It was like a barrier for us. Now that it's being dropped, what is nice is that we can now write the numerator and the denominator together. They each have the power n, so we can write them as a single fraction, a single ratio with the power n. And that's my next step. This is crucial because we know that the nth power and the nth root will undo each other, right? I'm showing it like cancellation, but you know that that's what's happening in the background. We don't usually show them cancelling off visibly like that. We have an understanding that they will undo each other. But just for us to see it visually, I have that. And now we have the root and the power. If they undo each other, they both are gone, leaving us with n squared plus 3n over 7n squared plus 5 for the limit. Now this makes it a lot easier because now we are ready to divide by n squared that will be limit n approaches infinity. N squared over n squared is 1 plus 3n over n squared is 3 over n over 7n squared over n squared will be 7 plus 5 over n squared because there's no n to cancel it. And now we're ready to apply the limit. When you apply the limit, you know that this will go to 0, this will go to 0, leaving us with 1 over 7. And that's beautiful because you got this clear-cut number. 1 over 7 is a fraction, and it's less than, it's a proper fraction, it's less than 1. And we have seen plenty of times by now that this would fall under the first condition because rho is less than 1. You know that the series will converge absolutely. So we'll come back and conclude here. We'll say since rho is less than 1, this complex expression here converges absolutely. We look at B. Okay, this is both complicated and cute. Look at this. It's summation n power n over ln n, natural log n, power n. too many n's there, but you know what they stand for. So let's focus on taking rho, which is because this is the root test. And let's acknowledge that an is n power n over ln n power n. Okay. So it's nth root of absolute value of n power n over ln n power n. We close the absolute value bar. Here again, we know that n is a positive integer. Right? So if you tried any positive integer for ln, right, and these are integers, so you'll have to start with 1, 2, and so on. So what is ln1? ln1 comes back as 0, right? ln2, try ln2. ln2 gives you a decimal answer, or a fractional answer, we could say, but then it's a positive number, 0.6931, and ln3 would be positive, so it's 1.09, and so on. So what you begin to see is, as you keep trying for different n in the ln, because other numbers are fine, n is positive integer, n power n is also positive integer, so the whole expression will be positive on the top. What's really problematic is that if you had ln n giving us a negative quantity, that will be a problem. But we know that this also is positive, and therefore its positive power integer will also be positive. This again allows us to drop the absolute value bars. So we'll say drop absolute value bars since the radicand is positive. Do not assume it's going to be this way all the time, so we have to test it. And once we are assured that it's okay to drop the absolute value bars, then you can have nth root of n power n over ln n power n. Now we know the drill. Because both the numerator and the denominator carry the same power, they can actually share the same power under a single fraction. So n over ln n power n for a common power. And then you know that the root and the power will undo each other. That gives us limit n approaches infinity. So first we dropped the absolute value bars, and then we took the common power n and then used that to undo with the root n. That leaves us with n over ln n. Okay. So here you cannot divide by n yet. You could do that. But if you directly applied n approaching infinity, you'll get an infinity over infinity condition. Okay. This would give us infinity over infinity condition, which is indeterminate. So we use L'Hopital's rule. Which allows you to take the derivative of the numerator over derivative of the denominator. So derivative of the numerator, derivative of n is 1, and derivative of the denominator, ln n, will be 1 over n. Okay. So I just want to quickly say this is coming from derivative of n, and this is coming from the derivative of ln n. Okay. Now we are ready to apply, basically you can simplify this. Because if you applied n approaching infinity here, you'll get 1 over 0 condition, right? So use the complex fraction technique to flip the denominator. multiplied to the numerator. So that would be limit n approaches infinity, n, and then when you apply n, the limit for n, you get infinity as the answer. This is totally fine. You can't just have infinity over infinity. And interestingly, we have not used this rule so far, but if you go back, I know it's way back. Oh, I went too back because I went all the way to ratio test. We have to stay here at root test. Root test, second condition says if rho is equal to infinity, then an diverges. Okay. So we come back and we say, since rho gave us infinity, because rho is on the left hand side. We started with rho. Look at this. We started with rho here, and we had to carry it through, right through, but we didn't. But we have that rho to be equal to infinity, which implies summation n power n over ln n power n diverges. Alright, so if I got a problem, a series, how do I choose the right convergence test? Okay. So we'll write a few hints here and see if we can remember to follow those hints and if those hints come in handy at all. So let's say choosing a convergence test. Okay, let's take a look at the first scenario that you might come across. Okay. So you want to ask yourself some questions. Is it a general one? Is it a known one? Your an, is it known? Meaning, if it's harmonic, right? Check if it's harmonic. You know, if it's harmonic, it diverges. Again, remember what harmonic is. Harmonic is 1 over n. Then see if it's alternating harmonic series. If it's alternating harmonic series, the sign alternates, right? And in that case, it converges. So you can directly use that knowledge without having to really prove it, right? So that's the reason we look for this. See if it is geometric series. We've seen this in a previous lecture too, right? And if that's the case, then you know there are rules. If your absolute value of r is less than 1, it means something. If it's greater than 1, it means something. Look for that. Likewise, see if it is p series. Here too there are rules, right? If p is less than 1, it means something. If p is greater than 1, it's something. Follow those rules. So collect those rules and follow them. 2. If your summation an is similar to a p series or a geometric series, it's similar, it's not the same, of course. Then what we suggest is go for a comparison test. Or a limit comparison test. There is a difference, so please go back and follow that lecture. We just did limit comparison recently, so you remember that. Go back and check on comparison test. In fact, we used that in one of our problems before. And if you come across an alternating series, right? If summation an is an alternating series, we saw that the alternating series test could be used. The test had 2 conditions, so if the 2 conditions we're satisfied, then you know it converges, the series converges. And you could use limit comparison or comparison test. To check for absolute convergence if you had absolute values. Yeah, you see the absolute value bars, then you want to try that. Now if your summation an contains factorial or power, we just saw that if it had power, like the n and the n, right? If it had the power, then it can undo the root, and so we would say, well, if your an can be written as something power n, then go for the root test. If not, go for the ratio test. And if you had, if they're just not working and you find that using a divergence test is better, go for it. And if you had no info when you did the divergence, then go for integral test. Okay, at the end of the lecture, I will provide, towards the end of the lecture, I'll provide a complete list, a table of all these series and tests and their conclusions, so that you'll have a way to have them all organized, especially all that we've seen in chapter 4 here. Okay. So let's take a look at the problem. We'll look at, say, 2 or 3 problems, even 4, to see if we can use these hints that we just saw to choose the right test. So determine if the series converges or not. So let's take a look at the first one. Summation n 1 to infinity n squared plus 2n over n cubed plus 3n squared plus 1. Take a look at this problem and determine which one it resembles. Now if you go back here, we're saying, well, does it resemble harmonic or geometric or p-series? No, it does not resemble any of those things. Is it similar to p-series or geometric series? Well, if you look at our problem, you could make it appear similar, okay? Meaning you can reduce it or approximate it to make it look like a harmonic, harmonic or a p-series. So if that's the case, then the second condition says, if it's similar, go for limit comparison or comparison test, okay? So in this case, limit comparison says, hold on to what you have and compare it with another series that you will generate, you will create, and then use the conditions that come under limit comparison test to see which one it follows. So then we can see that this n squared plus 2n over n cubed plus 3n squared, if you were to approximate this, right, meaning when we say approximate, we only focus on the leading terms. So n squared over n cubed, which will approximate to 1 over n. This is how I decide which corresponding series I could use to compare with this. So now we can use limit comparison test, because we've got the green one, which is given in the problem. We generated the pink one by approximating it, and then we use the limit comparison. Use limit comparison test. We like the limit comparison simply because of the limit, because you could then evaluate the limit 1. 2, because of all those conditions, right? You can get more information if it converges, diverges, and all that. And also, and thirdly, actually, to me personally, I like the ratio setup because it helps us to work with the limit. If the limit, when you apply it directly, gives you an indeterminate form, because of the ratio setup, you can use L'Hopital's rule and go further and complete the problem. So I like it for all those reasons. So the given expression goes up first, divided by our expression. If it helps, we could just say this will be our Bn, and this whole thing will be our An. It's always what comes in the problem, right? That's your An over the Bn, and that's what we have here. Now we have, oh no, that's n cubed, times n over 1, right? Multiply the numerator with the n so that you get, multiply across. There's nothing to factor out in the denominator. We could have to factor out in the numerator, but it doesn't really help us. Therefore, we're trying to distribute it, so they get n cubed plus 2n squared over n cubed plus 3n squared plus 1. If you have it in this form, we know the technique. The technique is to divide both up and down by n cubed, isn't it? So n cubed over n cubed is 1, plus 2n squared over n cubed is 2 over n. 2 over n, over n cubed over n cubed is 1, 3n squared over n cubed is 3 over n, plus 1 over n cubed. Yeah? Alright, now we know that when you apply the limit, as n approaches infinity, 2 over n approaches 0, 3 over n approaches 0, 1 over n cubed approaches 0. And that leaves us with just the 1. And we know that 1 is not equal to 0 because of you're using the limit comparison test. You will use the test to help determine that this actually is not equal to 0, means you'll have to see what happens to Bn. Okay, it's the second condition. Second condition says if the limit of that ratio An over Bn is not equal to 0, and if Bn series, summation Bn, diverges, then you have the original series also diverging. Okay? And so we have to now determine if summation Bn diverges. I apologize, I said the second condition, it's the first condition. Okay? Because I just quickly checked. The second condition for limit comparison theorem is if limit An over Bn equals 0 and Bn converges, then An converges. So I misquoted it. It should have been the first condition. This is the first condition because it's not equal to 0. It's a number that's not equal to 0. That means both An and Bn series converges or they both diverge. So then I come back here. Now we don't know anything about An, but we do know about Bn. Bn actually is the series Bn is 1 over n, which is a harmonic series. Summation Bn is a harmonic series, and we know harmonic series diverges. Okay. So we come down here and say, since limit An over Bn is not equal to 0 and summation Bn diverges. This implies the given series also diverges. I think I was numbering it as 1, 2, and 3, but I'm going to switch to A, B, and C. It's just easier. This way, we are not confused with any numbers that come in the problem itself. Alright, now this is a problem that appears to you, and we have plenty of tests, so which one do we choose? So if you go back to choosing the convergence test general idea, it says, look for all these things. What we have now is not similar to P-series or geometric series. It's an alternating series. Yes, it's an alternating series, right? You have the -1 power n plus 1. Okay, so keep that in mind. And the given problem also contains a factorial. It says if it's in the root form, then use the root test. But if it's the factorial, so let's come down here. Because it's alternating series, good. But then what is far more serious is that it's got the factorial, right? So we're going to focus on the factorial and say, well, the factorial implies ratio test, because that's where we use the factorial, right? And what's also nice about the ratio test is that it takes care of the absolute value. So you don't have to worry too much about the alternating series, because the absolute value will take care of the alternating signs and only stick to positives. Therefore, we can now we can safely use the ratio test and see if it works. Okay. So, you know, the row ratio test, so you can't really go wrong in this. You have to build a ratio. The ratio was an plus 1 over an. That's also nice because you don't have to come up with a new function, a new series. You can just use the same series that you have and add a 1 to it and then simplify it, right? So for those reasons, if you can identify the ratio test, it's a whole lot easier. And this time we were able to identify it easily because of the factorial. Okay, an is -1 power n plus 1 times 3n plus 1 over n factorial. That's given in the problem. An plus 1, again, tread carefully. Wherever you have n, you have to do n plus 1. All it takes is for us to put the wrong parentheses or fail to put the parentheses, and then we've lost it. So that's why I keep insisting on how careful we should be in watching out for the substitution. So here again, remember to distribute. I'll use a different color so it doesn't merge with what I've written. That's 3n plus 3, and then there is this plus 1. So that's going to be 3n plus 4. Okay. Over n plus 1 factorial. So we've got to an plus 1 kind of reduced. Let's come back here to the main step in green. Oops, n plus 2. All over an. Okay. You know the drill, so go ahead and you can pause the video at this point, do it ahead, and come back and check if our answers match. Because you're seeing this like for the third or fourth time, I'm going to simplify it as much as possible right in this step. this becomes positive 1. This is absorbed by the absolute value bars. So we have all those things there. That leaves us with so we can in the same step I can actually talk about the absolute value bars. So what we are left with is in the inside of the bars I have 3n plus 4 over n plus 1, right? And because of the absolute value bars, n being positive integer, you can drop the absolute value bars. And so I'm doing that also in this step. Okay. Oh, that's a 3n plus 1. I'm sorry. Missed the 3. And there was an n plus 1 and a 3n plus 1 in the bottom. Yes, that's better. So all the others cancelled off. Okay. Even then it doesn't change it because n is a positive integer. They're all pluses and they're all positive expressions, so the absolute value bar can be safely dropped. Now go ahead and distribute the denominator. Upon doing the FOIL, this reduces to plus 4n plus 1. Okay. Now you always divide by the highest degree in the denominator. So you divide by n squared, because you can think of this, right? If you divide it by n, which was in the top, right, then this will be on the top, it will be fine, but in the bottom, if you divide this by n, you'll still have a 3n, and we want the n's, all the n's, to go to the denominator. Therefore we choose the one with the highest power to divide. In particular, we do not want any n in the denominator. N on the, like you don't want a 3n to be left over. You want a 3 over n, that kind of a setup. So this division will take care of that. So 3n over n squared will be 3 over n plus 4 over n squared on the top, divided by 3n squared over n squared is 3 plus 4 over n plus 1 over n squared. Okay. And now let's apply the limit. So this will be a 0, 0, 0, and 0. So you get 0 over 3, which is 0. Perfectly fine. And then because we did the ratio test, so go to the correct test. The ratio test says if rho equals 0, then it implies that your given problem converges conditionally. Okay, here we have e power n over n cubed. And we said if this is not a geometric series, or, those are all ruled out just because of the e itself, right? The presence of an e eliminates all those possibilities. So then we come down to see the format. The format is this has a power. Unfortunately, the power format is not ideal because you want the same powers matching up and down in order to use the root test so that the power and the root will undo each other. So that is lost. So we do have the power, but that is not ideal. Now let's try the convergence test then. I apologize, the divergence, the convergence couldn't be established here with the with the root test. So try divergence test. If you recall, the divergence test is kind of simple. Okay. It says if limit n approaches infinity equals c, which is not equal to 0, or if it does not exist, dne, then limit n approaches infinity diverges. A very simple test, but this is a divergence test, so it only talks about divergence. So we could go ahead and try this, right? So if you, and we saw that if there was no information here, if we could not, say you got limit an to be 0, you can't use this test because then you violated the condition. In which case you'll have to go and use the integral test. So for now, we'll see if this works. Okay. So for us here, an would be e power n over n cubed. Okay. I'm sorry, not a power n, an is limit e power n over n cubed. Now in order to find the limit for this one, this is in the ratio setup, there are plenty of ways to approach this. So one is you could use the graph. Okay, you could look at the graph and determine what happens as n approaches infinity. Okay, so I have the graph for e power n over n cubed, because I can't put the n, I put the x in Desmos. What you'll see is you now have, as n approaches infinity, right, as we move towards infinity, you can see that your entire graph approaches infinity. The entire graph has two parts. If n approached negative infinity, you can see that actually your function approaches 0. But we are talking about n approaching positive infinity, which is to the right here, and therefore the function approaches infinity. So you can automatically determine that limit of e power n over n cubed is infinity using the graph. Okay. Or you could use, so I'll just say equals infinity from graph, which is very quick. You could use your graphing calculator. Or you could use the L'Hopital's rule, okay? Because when you plug in for infinity, you get infinity over infinity. And L'Hopital's rule would the first for the first iteration would give you e power n, derivative of e power n is e power n itself, over 3n squared. When you apply the limit, that becomes infinity over infinity. And then you apply L'Hopital's rule again. Derivative of e power n is e power n. But 3n squared becomes 6n. Again, you apply the limit, it gives you infinity over infinity. Apply L'Hopital's rule for the third time. You get e power n over 6. And when you apply the limit, e power n is going to be infinity, right, over 6. Again, how do I know e power n is infinity? Because e power x, think of the graph for e power x. Okay, let me show you that here. You know, e power x looks very much like your regular exponential function, but here also you can see e power x as x approaches infinity, e power x approaches infinity, right? And so you can recall from your exponential lessons that this is what happens. And come back here and you can see that that's another way to establish that the answer will come out to be infinity. You can use the graph, or you could use, you know, analytically, you could use L'Hopital's rule and get that same information. Nevertheless, because you got these two to this to be equal to infinity, right? You'll have to now use where are we? Yeah, so now we got this equal to infinity either from the graph or from the from L'Hopital's rule. Okay, so then we can say limit n approaches infinity, dne does not exist, which implies by the divergence test, summation the series. What was the series? Summation e power n over n cubed n1 to infinity diverges. Okay. Summation 1 to infinity 3 power n over n plus 1 power n. Okay, this is interesting because this has the power n up and the power n down. You know, that's a very striking clue for us to use the power as the clue for using root test. So power here, we couldn't use that previously. Even though we saw the powers weren't the same up and down. But here the powers match, so you know that you could use the root test. And so let rho be limit nth root of absolute value of an you can see the appreciation here for limit laws. Limit laws allowed us many things, and this is again the reason how you were able to overcome radicals and all that. In limit laws it said, well, you can bring in the limit inside the radicand. Here an extension here would be the root test, where we are able to take the nth root of an, which inside contains the power n. Okay. Now again, investigate. Your n is a positive integer, so n plus 1 will be a positive integer. So things are good here. We can drop the absolute value bars. Okay. And then that would be limit n approaches infinity nth root of 3 over, again we've seen this before, so I'm going to use that in one step. I'm dropping the absolute value bars as well as combining the power n for the common ratio for 3 and n plus 1. And then we know that the root and the power will undo each other. That will leave us with limit n approaches infinity 3 over n plus 1. Okay. As always, you want an n in the denominator. So divide by n. You know that you're dividing by n just because n is the highest power in the denominator. Right? So divide by n, and that will give us 3 over n over 1 plus 1 over n. And we know that this, when you apply the limit, this becomes 0, this becomes 0. So you get 0 over 1, which is 0. And if you go back to the root test says if rho is 0, that's the first condition, it implies that the series converges absolutely. With that, we come to the end of the lecture. I do have a summary of all the series and tests and what conclusions we'll give, which you can watch right after this. So I'm going to display that. There will be no lecture explaining these things. It's just for you to view. Okay. So here we see the table with series, conclusions, and comments. I will just go by each test and I'll let you read through it. We have the divergence test. Then we have the geometric series. If you feel I'm moving too fast, you can always pause the video and read it. Well, geometric series has the rules based on R. We have the P series. Again, we have the rules based on P. And remember, when P is equal to 1, it's called the harmonic series. The P series will be called the harmonic series. So harmonic is a special case of P series. You have the comparison test. You will compare the given series with a known series. We have the limit comparison test. Here too we do a comparison, but this time we set it up as a ratio, limit of the ratio. We have the integral test. As the name says, there will be an integral. You'll use this test when you know that your function can be easily integrated. There's an integrable function, and you have these conditions, of course, that it's positive, continuous, and a decreasing function. Then an and fn can be matched, so that you could use integration to decide if the series converges or diverges. Then you have the alternating series. As the name says, it can be applied only to alternating series, provided the conditions satisfy, and this will prove convergence. We have the ratio test. We have three conditions that helps us to understand absolute convergence, divergence, or inconclusive if rho is 1. We use this when we have fractions or exponentials. Root test is used when you can express your given series as a power n, both up and down if it's a fractional form, so that we could undo that power n with a root n that this root test allows. So I hope that you like this snapshot of all that we've seen, all the collection of tests. This will come in really handy with the next calculus course as well. So it's a good idea for you to have a look at this and take notes and copy it down so that you have them all handy in one place. So I hope you enjoyed this, and I will see you in the next video.